Hello all, welcome to this next session in the course. So this would be the fourth session in the course, and then so in front of you can see group data. So again, if you vaguely remember, we exactly stopped here in the third session. Okay, so we'll sort of extend from the same idea where we stopped in the last session, and then again sort of before we elaborate on the graphs associated with the group data, we'll again sort of quickly revise as to where we stopped. Okay, so in the last section, if you remember, we talked about descriptive statistics more from a graphical point of view or plotting point of view. So we started with line graph, then we talked about bar graph, right? Then we talked about a frequency polygon, and similarly we talked about advantages and disadvantages of each graph as opposed to the previous one. Then we talked about categorical data, if you remember the disease data, so diabetes, hypertension, heart disease, stroke, etc. So that data set was a categorical data set. The very first data we talked about was the starting salary data set, which was a numerical data set. So again, if you remember, for a numerical data set, line graph, bar graph, frequency polygon makes sense, right? But the moment you transition into categorical data set, then the graph which is required or the most famous is a pie chart. So we talked about a pie chart, and right towards the end we talked about group data. So how do you create a frequency table for a group data, and this is exactly where we stand as of now. Okay. So again, if you vaguely remember the example we started with, so I just have this starting slide just to tell you the frequency table with the group data, but what exactly is the data set here? So if you remember from the last session, we talked about a data set which contains the lifetimes of 200 lamps. Okay. So all the values in the data set correspond to lifetimes of 200 lamps, and if you remember, you had a very large table containing the lifetimes of all the 200 lamps, right? And then I think we also discussed the fact that you have to somewhat create some classes depending on the minimum lifetime and the maximum lifetime. So look at the entire data set, identify minimum, identify maximum, and then somewhat create a range. So in this case, the range is 500 to 1500. So the minimum would lie somewhere in the first class, 500 to 600, and the maximum might lie somewhere in the last class, so 1400 to 1500. So once you fix all the classes, and then as of now, just for no discrepancies, no fancy things, we'll have equidistant classes. So equidistant means the length of each class should be same. So in this case, the length of each class is 100. So 5 to 600, 6 to 700, 7 to 800, etc. And then correspondingly, I have a frequency column. So for example, is 25, what do you mean by 25? So 25 means in the entire data set containing 200 lamps, you have 25 such lamps whose lifetimes fall in this range, so 800 to 900 hours. So again, remember that all these numbers, they are in hours. So 800 hours, 900 hours, 1000 hours, etc. Okay. So this is the meaning broadly of the data set, and how exactly have you created the frequency table corresponding to the group data. So now what next? So what kind of a plot or what graphical technique can we have from such an instance? So we can actually create a histogram. So again, you might have heard about histogram very often. So histogram is kind of the very first or one of the very first plots that analysts draw, right? So histograms are kind of meant for group data. So here, how exactly is a histogram different from a bar graph? Because again, in a bar graph, you vaguely remember we had bars, right? So the major difference in a histogram is that histogram you have classes. So here if you see, you have bars, but bars correspond to a class, and bars don't correspond to individual values. Okay, so in a bar graph, you will remember each bar corresponding to individual value on the x-axis, which is not the case here, right? So if you see on the x-axis, what we have in the x-axis, we have lifetime, so life in units of 100 hours, and similarly on the y-axis, we have frequency or number of occurrences. So the idea of creating a graph is somewhat similar to a bar graph, but a major difference is that if you look at the x-axis, all the bars, they correspond, or rather they span a class rather than individual lifetimes. Okay. For example, the first graph spans 500 to 600 hours, the second bar spans 6 to 700 hours, all the way up to last, which spans 1400 to 1500 hours. Okay. Alright, so again, couple of very advantageous things about histogram is that you can see the shape and roughly the density or the behavior of the data set. So if you somewhat connect the top ends of each graph, I can somewhat get a curve which tell you the behavior or rather the shape of the data set. Okay. So, in this case the shape is somewhat symmetrical. So, can you see that? So, on the lower end and the higher end you have very less values, whereas in the middle you have a larger chunk. Okay. So, symmetric means what? Symmetric means you have a peak in the middle and you have roughly equal tails at both the ends. Okay. So, what exactly it means is that you have bulbs or you have lamps having lifetimes which are either very low on the left hand or either very high, and those number of bulbs are not that much. So, the number of bulbs having lifetimes either very low or very high are less in number. Okay. For example, again if you vaguely remember the last frequency table, then 500 to 600 hours you only had 2 such lamps. Okay. So, we can very well go back. So, for example, 1400 to 1500 you only have 1 lamp. Okay. So, all these frequencies are nothing but plotted on the histogram. So, for example, 900 to 1000 you have lot of lamps, 60 lamps or rather close to 60 lamps, right. Similarly, 1000 to 1100, 1100 to 1200 you have lot of lamps. So, close to 40, close to 45. Similarly, towards the lower end and the higher end you do not have many lamps. Alright. So, this is broadly a structure of a histogram. How exactly do you plot a histogram? What advantages a histogram offers as opposed to bar graph, line graph, pie chart or any other plot we saw earlier. So, again just to repeat, the histogram contains group data or histogram represents a group data as opposed to a bar graph. So, even in a histogram you have bars, but those bars do not correspond to individual observations, they rather correspond to some classes. Now, the next thing is cumulative frequency. So, again from a group data perspective, what exactly you mean by cumulative frequency? So, we will spend some time on cumulative frequency, understanding cumulative frequency, etc. Okay. So, again let me go back to the earlier data set. So, this was the earlier data set, right. Now, what exactly to do is you have to first convert this frequency column to relative frequency column. Okay. And then how do you do it? So, do you remember n? So, n in this example was 200 because the data set focuses on 200 lamps or lifetimes of 200 lamps. Okay. It says right here. Okay. So, now for converting a frequency column to a relative frequency column, I have to divide each value by 200. So, 2 by 200, 5 by 200 and the last one would be 1 by 200. Make sense so far? So, 2 by 200, 5 by 200, 12 by 200, 25 by 200 all the way up to 1 by 200. So, once you divide each number by 200, you will end up getting a relative frequency column as we got even earlier in the last session. And now what you do is you have to cumulate the relative frequencies one by one. So, cumulating means what? You keep on adding the relative frequencies one by one. Okay. So, again just to explain, so the first relative frequency is 2 by 200 and then this is roughly 1 by 100. So, this would be 0.01, right. Next relative frequency is 5 by 200. So, this one is 2.5 by 100 which is 0.025. Okay. So, the first one is 0.01, second one is 0.025. So, how do you accumulate these? So, the first cumulative frequency would be 0.01, second cumulative frequency would be sum of these two. So, 0.01 plus 0.025 which happens to be 0.035 and so on and so forth. So, you basically add each and every relative frequency to the last sum and then sort of cumulate. Okay. So, again one open question to all of you, you can pause the video and try to answer that what would happen if you go and do this to each and every relative frequency. So, what would be the very last cumulative frequency? So, once you will end up getting here the last point or the last class, what would be the very last cumulative frequency? So, the very last cumulative frequency would always be 1, right, because you will be adding all the relative frequencies before that. Okay. Now, again let's move to the cumulative frequency chart and this is exactly what you are plotting. So, once you get the cumulative frequency column from the relative frequency column, then you basically simply plot each and every cumulative frequency corresponding to the class. So, for example, 500 to 600 would be 0.01, then 6 to 700 you'll increase, then again you'll increase, then again you'll increase, and eventually if you see it converges to 1. So, the last value has to be 1. Alright. So, how do you connect the dots? So, a cumulative frequency as opposed to relative frequency or simply a frequency means that once you have a cumulative frequency column, then you simply plot the values on the x axis and then correspondingly the value would range from 0 and then it will converge to 1. Okay. So what might be an advantage of a cumulative frequency as opposed to relative frequency or frequency is that we can sort of identify time points where the activity sort of picks up. Now what exactly I mean by activity being picked up is that if you observe this point, so can you see a steep rise in the cumulative frequency chart after that point, which means that more and more number of bulbs having a lifetime of, let's say, at least 800 hours are there in the data set. So from 800 hours all the way up to roughly, let's say, 1100 or slightly more than that, you have larger chunk of the data set, since the cumulative frequency is being picked up from 800 to all the way up to 1100. But after 1100, if you see, the line sort of converges and converges to 1, which means that there are not very much lamps, or very few number of lamps have a lifetime having a lifetime of, let's say, more than 1100 hours, or let's say 1150 hours and so on, and ultimately it should converge to 1. So when you have lamps which are, let's say, having lifetimes more than 1400 hours or close to 1500 hours, you don't have that many number of lamps because the relative frequency is almost converging to 1. Okay. So again, like I said, these are some advantages which a cumulative frequency chart offers as to what a line graph or a bar graph or a frequency polygon or histogram or pie chart, they do not offer. Alright, so now we will talk very briefly about quite an interesting sort of a plot called a stem and leaf plot. A slightly different plot which people don't analyze that much, but we will talk very briefly about what exactly are the ingredients required to create a stem and leaf plot. So again, as the name suggests, this plot contains two things, so a stem and a leaf. Okay. So imagine that you have a tree and you have a lot of stems and then you have leaves protruding from the stems. Okay. But what kind of a data set will analyze? So we will analyze this data. So the following table gives the monthly and yearly average daily minimum temperatures in 35 US cities. Okay. And we will only focus on annual average, so the yearly averages. So if you see the very last column, is slightly hard to identify the observations, but you may zoom in if you want and do all sort of things, but the last column kind of gives you the yearly average temperature values for 35 US cities. For example, 57.4, 34.1, all the way up to 33.1, and remember that all these temperatures are in Fahrenheit, of course. So 57.4, then let's say 51 corresponding to, let's say, Little Rock, then Los Angeles, Sacramento, San Diego, San Francisco, all the way up to St. Louis, Great Falls, etc. Alright, so data set contains 35 US cities and their corresponding annual average minimum temperatures. So all these are minimum temperatures in Fahrenheit. And now our goal is to somewhat create a stem and leaf plot from the data set that we have. So now this is exactly a typical stem and leaf plot. So again, like I said, it contains two parts. It contains a stem, which is there in the first column, and it contains all the leaves. So all the values you see on the right side of the vertical line are called as leaves. Okay. So these are the leaves in the data set, and this portion of the data set is nothing but the stem. Okay. Now how exactly should you read this? So the first column gives you the starting number, or rather the starting digit of any number, for example 7. And then you somewhat go through the entire row and read each number and sort of attach that. So the first value becomes 70, second value becomes 69, then 51, 51.3, 52, 55.5, 57.1, etc. Now again you can come down, the stem is 4, then the first value is 40, 41, 42.4, if you come down the line, let's say 49, 49.2, etc. Then again if you come one level down, then the stem portion is 3, then how should you read this number? 33.1. So you simply attach the leaves to the stem and treat it as a single number. So 33.1, 34.1, 35.3, all the way up to 39.5, and lastly 29, 29.8. Okay. So stem and leaf plot is not very difficult to sort of create and sort of understand. The left portion corresponds to the stem, while each and every value that you see on the right side of the vertical line corresponds to the leaf part. Okay. So you take the stem, you attach the leaves and treat it as a single number, and then that single number becomes an observation. Now what might be a couple of advantages very quickly of a stem and leaf plot? So again, I can somewhat treat a stem and leaf plot as a horizontal sort of a histogram. So can you see that? So if I flip this vertically, it becomes a histogram for me, or it sort of becomes a bar graph for me, isn't it? So again, from a stem and leaf plot, I can sort of identify the stem, or rather the region where more number of observations are lying. For example, you have more number of observations starting with 4, okay, or you have more temperature. So again, remember that the entire data set is for the minimum annual average temperatures of 35 US cities. So hence, there would be more number of US cities having minimum temperatures starting from 4, or rather starting with, let's say, 5 or 3, as opposed to there would be very less number of US cities where the minimum annual average temperature starts with a 7. So you also have a 70 in the data set, but only one number corresponding to 7 as a stem. Okay. So a stem and leaf plot kind of gives me couple of extra things which probably a frequency table or some other graph might not give me, is that it sort of tells you a rough behavior of the data set as well, or a rough shape of the data set as well, because you can sort of treat a stem and leaf plot as a horizontal or a sleeping bar chart. So for example, you have more number of values falling in this range or that range, etc. And again, if you look at both the extremes, so starting with 7 or 2, you have lesser number of US cities whose temperatures start with, let's say, 7 or 2. Okay. So again, down the line we'll again create an example or talk about an example which talks about a stem and leaf plot, and there again I'll try to elaborate a bit more. Okay, so having said that, so far we've talked about, let's say, multiple plots, charts, graphs, etc. Okay, so now this next portion of the next session talks more about further descriptive. So what exactly can we have a bit more or bit added on to the graphs or plots or charts that we have created beforehand. Okay. So further descriptive means what? So further descriptive means nothing but we'll talk very briefly about the summary variables that we've talked about in the last session as well. So mean, variance, standard deviation, median, mode, etc. Okay, so the very first summary variable which probably almost all of you would understand or would have read or would have calculated on your own is a sample mean. Okay, a sample mean or the sample average, etc. So mean also corresponds to nothing but the average of a set of numbers. Okay. And again, how do you find it out? So you have a simple formula. So depending on how many numbers you have, so depending on the sample size, which is n, you will basically have a sample containing n observations. So you basically simply add all the numbers and divide by n. Okay. So the sample mean denoted by x bar. So x bar is a very famous or a standard notation to denote the sample mean. X bar is defined by, so x bar is nothing but summation of xi divided by n. And what exactly are xi? So xi is nothing but each and every ith observation you have, I running from 1 to n. So very quick example, if you have a data set containing 5 numbers, you simply add all the 5 numbers and divide by 5. Okay. Now, a couple of properties of a sample mean. So imagine that you make a small transformation. Okay. So initially, what is the variable you have? So the variable is xi that you have. Now imagine that you simply multiply each xi by a constant a and add a constant b. So a and b are some constant numbers. So let's say 2 and 5 or 5 and 10, etc. And this new transformation I am calling it as yi. Okay. And yi is what kind of a function of xi? So yi is simply a linear function of xi. So linear means what? You are multiplying by a constant, adding a constant. So you don't have any higher powers. Okay. Then the sample mean of this data instead. So earlier we found out the sample mean of xi, which is summation xi by n. Now if you transform xi is using a linear function, something like a xi plus b, then the sample mean of this data now, y1, y2, y3 all the way up to yn is given by y bar, which is again, if you apply the formula blindly, you will get summation of a xi plus b divided by n. And here I can sort of bring out a few constants, I can bring in the summation sign, I can sort of play around with the summation and the linearity aspect and ultimately get this. Okay. So this is kind of a property, right. So y bar equals nothing but a x bar plus b. So the only thing in order to find out the mean of the transformed variable yi is nothing but input this x bar here in the function, multiply x bar by a and add b. Okay. So your initial yi was what? So yi was a xi plus b, and now if you want to find out y bar or the sample mean of this transformed variable yi, the only thing to do is you have to multiply a by x bar. So find out the sample mean of xi values first, that would be x bar, multiply by a and then add b. Okay. So again, like I said, these are some corollaries, these are some properties related to the sample mean. Even if you transform the sample mean using a linear function, adding some constants, multiplying by some constant, then how do you find out the mean of the transformed linear function? Now, the next thing is sample mean for frequency based data. So, again assume that you have a data set which is presented in a frequency table. So, again to go back to the last session to understand how a frequency table looks like. So, the first column contains the observations and the second column contains the corresponding frequencies. Okay. So, assume that these are the observations V1, V2 up to Vk, and the corresponding frequencies are nothing but F1, F2 up to Fk. Okay. So, assume that you have a data set which is presented in a frequency table kind of a format where you have Vi's and you have the corresponding Fi's. Then in such a situation, how do you find out the sample mean? So, you have a simple formula to do it. So, sample mean in this case is nothing but summation Vi into Fi. So, you multiply the observations and the corresponding frequencies. So, Vi into Fi divided by n, and again n is what? N is the sample size, and in this case I can actually write down n, which is nothing but summation Fi, okay, I going from 1 to n. So, if you add up all the frequencies, so if you do not know as to what n is right in the beginning, you can basically add all the frequencies and summation of all the Fi values is nothing but the sample size. Okay. So, this n that you see here you can actually get using adding all the frequencies. So, ultimately what is the formula? Formula is nothing but summation Vi, so observation into the corresponding frequency divided by summation of Fi or divided by n. Okay. So, slightly different way of finding out the sample mean if the data set structure itself is presented in a frequency table rather than you are presented in a single vector kind of a format. Couple of quick examples. So, this data set that you see here are nothing but winning scores in a US Masters golf tournament during 1982 to 1991. Okay. So, this US Masters golf tournament happens annually, and all these are the winning scores in the corresponding US Masters golf tournament starting with year 1982 all the way up to 1991. So, 284, 280, 277 and last one is 277. Now, idea is find the sample mean of all these scores. Okay. So, firstly how many values you have? So, you can simply count, right. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, you have 10 values. So, n is 10. Okay. So, n is 10. So, what you do is you simply add up all these scores. So, 284 plus 280 plus 277 dot last one is also 277, and then simply divide by the number of observations you have, which is 10, and this would give you nothing but x bar. Okay. So, x bar equals summation of all the observations divided by 10. Now, a second example having a frequency table kind of a format. So, again the following is a frequency table giving the ages of members of a symphony orchestra for young adults. So, the first column gives you the age, so 15, 16, 17, 18, 19 and 20. So, again these are the ages of members of a symphony orchestra for young adults. And then how many members are there having those ages? So, in the orchestra you have 2 people having age of 15, you have 5 people having age of 16, and similarly you have 13 people having age of 20. So, now the question is find the sample mean of all the ages of the 54 members of the symphony. So, it tells you n here, so n is 54, this is my sample size, and now the finding the sample mean of a sort of a frequency table format or a data set containing a frequency and an age column is nothing but you apply the second formula. So, summation Vi into Fi divided by n. So, here what you do is you simply multiply the corresponding age by the frequency. So, 15 into 2. So, this would be what 15 into 2 plus 16 into 5, etc., etc. Last one would be 20 into 13, and then since you already know n, you divide by 54, which is n. Okay. So, again like I said, finding sample mean is not very difficult if you understand that whether the data set is in the form of vector, a single vector, or a frequency table sort of a format. Okay. Okay. So, now we will spend very brief time on understanding sample median. So, what exactly is a sample median? So, sample median is nothing but the middle point of any data set. So, let us say if the data set contains 10 observations or 11 observations, you basically sort the data from smallest to largest and find the midpoint of the observation which stands right in the middle of the data set. So, that middle observation is called as a median. Alternatively, a median is what? So, median is nothing but 50% of the data set should be less than the median, and the remaining 50% of the data set should be above the median. Okay. So, this is the idea of a median. So, median is that observation which divides the data set into 2 equal halves. Okay. And these are roughly the steps to find out the median. So, the very first step is ordering the data. So, you simply order the data or put all the observations in an increasing order, so smallest to largest. Now, couple of situations. So, depending on whether n is odd or n is even, you have different formulas to find out the median. Okay. So, now if n is odd, you have a clear midpoint, isn't it? So, let us say if n is 5. So, the third observation is the midpoint, of course, once you sort the data. Okay. So, if n is odd, the sample median is nothing but the value at this position. So, n plus 1 by 2. On the other hand, what would happen if n is even? So, if n is even, you have two midpoints, isn't it? So, let us say if n is 6. So, if n is 6, then the third and the fourth value are the midpoints. So, in that case, what you do? You simply take the average of the third observation and the fourth observation. So, essentially, you are taking an average of values and positions n by 2 and n by 2 plus 1. So, you have a small typo here, it should be n by 2 plus 1. So, at positions n by 2 and n by 2 plus 1. So, ultimately sample median is thus the middle value when the data set is ordered in some increasing order. Okay. So, again in simple example, you can pause the video, try this example at your own end. So, here what you should do is you have a frequency table kind of format. So, you have ages and the corresponding frequencies, again the symphony orchestra example. So, here I might as well write down all the ages. So, the first age is 15, frequency is how much? 2. So, there would be repetition of 2, then the next number is 16, then 16 how many times? 5 times, right. So, this would be 16, etc., etc., and last one is 20 repeated 13 times. Okay. So, once you have this entire data set, then you find out what n is. So, I think n was 54 if I vaguely remember. So, since n is even, then what should you do? So, you should take the average of these two numbers. So, at positions n by 2 and n by 2 plus 1. So, n by 2 happens to be 27. So, 27 and 28. So, observations at these two positions, you take the average of that and that would be the median. Okay. So, now this is the idea. So, descriptives is nothing but plots, but they also contain some summary variables like mean, median, etc. So, now in the next session we will try to elaborate this and we will try to finish off with descriptives, and then we will talk about a practical example as to how do you find out mean, how do you find out median, variance, etc. and then we will close the session at that. Okay. Thank you.